Good morning, this is Dr. Kumar Arya, Associate Professor in Department of Chemical Engineering, IIT Jalandhar. Today I am going to explain power law of fluid flow in a plane narrow slit. So the narrow slit is given by something like this. So this is what you have, a narrow slit here, which is 2b distance apart, and these are two parallel plates here, one is here, one is here. The width of the plate is W and length of the plate is L. The pressure at the inlet end is P1 and exit is P2. So now the problem statement is: consider a fluid of density rho is incompressible laminar flow in a plane narrow slit of length L and width W, formed by two flat parallel walls that are distance 2b apart. End effects may be neglected because B is less than W and W is less than L. The fluid flows under the influence of pressure difference delta P, gravity, or both. Determine the steady state velocity distribution for a non-Newtonian fluid that obeys the power law model, example a polymer liquids. Second, obtain the mass flow rate of a power law fluid in a slit flow. So this is x momentum balance, that rho del u upon del t plus mu del u upon del x plus v del u upon del y plus w del u upon del z equal to rho gx minus del p upon del x plus del tau xx upon del x plus sigma del tau yx upon del y plus del tau zx upon del z. Now for steady state, this time derivative would be 0. Fully developed flow in x directions, del u upon del x is 0. V and W are 0. Flow is totally one dimensional in x only. Now this term is 0 because del u upon del x term is 0. Then del tau x, del tau zx upon del z is 0 as compared to del tau yx upon del y, because the magnitude of del tau zx is always, delta z is always higher than delta y, so therefore this total value would be high magnitude by as compared to this one. So del tau yx upon del y equal to minus rho gx del p upon del x. So this is equal to delta p dash. Now we can integrate that. Tau by x equal to delta p dash y plus c1. Now we can put a boundary condition at y equal to 0, tau by x equal to 0. So that is at the center. So at the center of the slit you have 0. So we can calculate c1 equal to 0. So tau by x equal to delta p dash y. Now yx is eta del u upon del y to the power n equal to delta p dash y. So we can calculate here by integration here. So this is u equal to delta p dash upon eta 1 by n y to the power 1 by n plus 1 upon 1 by n plus 1 plus c2. Now we have another boundary condition, that y equal to plus minus b, u equal to 0, that no slip boundary conditions. So substituting that here in equation number 2, we can get this c2 equal to minus delta p dash upon eta to the power 1 by n, b to the power 1 by n plus 1 upon 1 by n plus 1. So here we will get u expression by substituting the value of constant c1 and c2. So this final expression for velocity is minus delta p dash upon eta 1 upon n b to the power 1 by n plus 1 upon 1 by n plus 1, 1 minus by upon b 1 by n plus 1. So this is expression is valid from 0 to y to b actually. Now at y equal to minus b, u equal to 0, we can check it here by substituting here. So y equal to minus b, we have substituted here. So we are finding the C3 is this one. Then sorry, we are substituting here, so we will get another expression for this. So here at no change in previous equation, this only place of y you are putting here minus b and minus y only. Rest is same as this one, everything is same. So here minus b, here minus y. So hence your velocity expression can be given by u minus delta p dash upon eta 1 by, to the power 1 by n, b to the power 1 by n plus 1. So there is mode of b upon 1 upon n plus 1 bracket 1 minus mode of y divided by b to the power 1 by n plus 1, where mode of y is less than or equal to b. Maximum velocity at y equal to 0, so is this one minus delta p dash upon eta to the power 1 by n, b to the power 1 by n plus 1 bracket 1 by n plus 1. Volumetric flow rate q is given by q dash, so q is minus b to b, 0 to w u dy into dz. So 2w equal to 0 to b minus delta p dash upon mu 1 by n, b to the power 1 by n plus 1 upon 1 by n plus 1 bracket 1 minus by upon b to the power 1 by n plus 1 into dy. So integrating this term, we will get this equation first. After that take this common here, this term, simplify it here. So substituting the limit, so limit you have substituted, you will get this equations. After that another term here by taking the LCM, simplifying it further, so you will get q equal to minus 2w delta p dash upon mu to the power 1 by n, then b to the power 1 by n plus 2 upon 1 by n plus 2. Average velocity q by a, so we have already calculated q. A is minus b to b, 0 to w, dy into dz. So average velocity comes out to be that minus delta p dash upon mu to the power 1 by n, b to the power 1 by n plus 1 divided by 1 by n plus 2. For Newtonian fluid n equal to 1, so your average velocity is minus delta p dash upon mu b square upon 3. So thank you. This is all about the power law fluid flow in a plane narrow slit.